Good day, everyone. In this video, I will be talking about polynomial functions. So, our only objective in this lesson is to determine the rational roots of a polynomial using factor theorem or syntactic division. So, I hope that you guys still remember how to do those. But before we actually get into determining the rational roots of a polynomial, it is important to know about the Descartes' rule of signs. You might be wondering, why do we have to learn this first? Well, you don't have to, but this is actually good to learn because it will make the process of determining your rational roots a lot easier. You will understand more why this is the case later on the video. So, the Descartes rule of signs state that the number of positive roots of a polynomial function is either equal to the number of variation of signs in f of x or less than that number by an even integer. On the other hand, the number of negative roots of a polynomial function is either equal to the number of variation of signs in f of negative x or less than that number by an even integer. Okay, I know that what I said sound like mumbo jumbo to you, or in other words, very confusing. So let me show you an example of a polynomial function. So we got here x cubed minus 5x squared plus 2x plus 8. So we need to find the number of possible rational roots in this polynomial function. So what we do first is, it states here that the equal to the number of variation of signs in f of x. So we need to find how many variation of signs are there in this polynomial function. And as you can see here, this is positive x cubed and this is negative 5x squared. There is one variation of signs here because it's from positive to negative. Same here, negative 5x squared, positive 2x. This is one variation of signs because it's from negative to positive. But from here, positive to positive, there's no variation of signs here because it's from positive to positive. So we can assume that there are two possible positive roots. But this is still not yet the case. Remember that it is less than that number by an even integer. So that means that we have to minus 2 our possible positive roots by 2 since 2 is an even integer. So what is 2 minus 2? It's 0. So we also place here 2 or 0 possible positive roots. Okay, so we are not done just yet. We still have to find the number of negative roots of this polynomial function. So to do that, it says here that is either equal to the number of variation of sides in f of negative x. So what we do is we substitute x with negative x. After that, we will simplify this. Okay, so I want to address this part. So I see that some students will just place positive 5x squared because negative 5 times negative x is equals to positive 5x, right? But you have to take note of the exponent. Remember that negative x times negative x is equals to positive x squared. So the answer to this is still negative 5x squared. Okay, now that we are done solving this, we can now do the same on what we did here, trying to find the variation of signs. So negative to negative, there's no variation of sides here. From negative to negative, there's no variation of sides here. And from negative to positive, there is one variation of sides here. So we can conclude that this polynomial function has one possible negative root. I hope that you guys are still following. Okay, so now that we are done finding the possible positive roots and the possible negative roots of this polynomial function, we can now proceed to finding the non-real roots of this polynomial function. So first of all, we have to make a table. This is for the possible positive roots. This is for the possible negative roots. This is for the non-real roots, and this is for the total. And as you can see here, we have 2 or 0 possible positive roots. So we also place here 2 or 0. As for the possible negative roots, since there's only 1, we also only place 1 here. As for the total is the highest degree of the polynomial function, which in this case, it's 3. Now, the possible positive roots and the possible negative roots and the non-real roots should all add up to 3. So 0 plus 1, that's 1. So we need 2 so that it will add up to 3. So our other non-real root is 2. For this, 2 plus 1 is equals to 3. So there's no need for more non-real roots. So it's only 0. Okay, so now that we are done discussing the Descartes rule of signs, we can now proceed to rational root theorem. So the rational root theorem states that the possible rational roots of zeros of a polynomial function must be equal to a factor of the constant term, which is the p. The p is the factors of the constant term. So to a factor p of the constant term divided by a factor q of the leading coefficient. So q is the factors of the leading coefficient. In simpler terms, the possible rational roots are equal to p over q. So to understand this concept better, I provided the same polynomial function that we used to solve earlier. So it states here that p is the factor of the constant term, and our constant term is positive 8. So what are the factors of positive 8? It's plus minus 1, plus minus 2, plus minus 4, and plus minus 8. So you might be wondering why we have to add plus minus. It's because 1 times positive 8 is equals to 8. Same goes for negative 1 times negative 8. It's equivalent to 8. Or positive 4 times positive 2 is equals to 8. Or the negative versions of it. That is positive 8. So you get now why there is a plus minus. Now for the q, that is the leading coefficient, and our leading coefficient is only 1, so our only factor for it is also only 1. Now, it says here, the possible rational roots are equal to p over q. So we have to solve for this. So our first one is plus minus 1 divided by plus minus 1. That is equals to plus minus 1. I will speed up the video so that you won't get bored, but I hope that you understand this all. Okay, so now we have 8 possible rational roots. Why did I say 8? It's because there's 1, negative 1, positive 2, negative 2, and so forth. So we have 8 possible rational roots. Now that we know what the possible number of positive and negative roots there are, and the possible roots of that polynomial function, we can now use this information to find the actual roots of the polynomial function. And to do that, we need to use either syntactic division or factor theorem. So to find the actual roots of this polynomial function, we have to use either syntactic division or factor theorem. In this case, we will be using syntactic division. But I will show you how to use factor theorem later on. So our divisor will be the root we will be checking. And as you can see here, these are our roots. Plus minus 1, plus minus 2, plus minus 4, and plus minus 8. Let's try positive 1. So bring down 1. 1 times 1, that's equals to 1. Negative 5 plus 1, that's negative 4. Negative 4 times 1, that's negative 4. 2 minus 4, that's equals to negative 2. Negative 2 times 1, that is negative 2. And 8 minus 2, that is 6. So as you can see here, there is a remainder. And if there is a remainder, then that is not a rational root of this polynomial function. So we can say that 1 is not a rational root. Okay, so we know that 1 is not a rational root of this polynomial function. So we have to try to find the other roots. So we can try to use positive 2. We just do the same process, but with 2 as the divisor. As you can see here, 8 minus 8 is equal to 0. And there is no remainder in this root. So 2 is a rational root of this polynomial function. Now let's try 4. As you can see here, 8 minus 8 is equals to 0. We can say that 4 is a rational root of this polynomial function. And you might be thinking to yourself that you should solve for 8. Maybe it's a rational root. But remember that in here, there are 2 possible positive roots. So we don't have to solve for another positive root because we already have 2 and 4. So that's the importance of the Descartes rule of signs. They can save you a lot of trouble. You won't have to solve for every possible rational root, and you can save a lot more time. Now for the negative roots. So let's try negative 1. So as you can see here, 8 minus 8 is equals to 0, and negative 1, this doesn't have a remainder. So negative 1 is a rational root of this polynomial function. And remember that this polynomial function has only one possible negative root. So without the Descartes rule of signs, we would have been wasting a lot of time in here. Now, we just have to write our final answer. So 2, positive 2, positive 4, and negative 1. These are our rational roots of this polynomial function. Okay, so to recap, let's take on another example. So first, remember that we have to do the Descartes rule of signs. So for the possible number of positive roots, this is positive x cubed. There is a variation of signs here since it's positive to negative. There are no variation of signs here because it's from negative to negative, and negative to positive, there is one variation of signs here. So we can say that there are 2 or 0 possible positive roots. Remember 0 because 2 minus 2 is equal to 0. Now for the possible number of negative roots, you have to substitute x with negative x. And we have to simplify this. Okay, so remember that this is not positive x squared but still negative x squared because negative x times negative x is equal to positive x squared. And you multiply that with a negative sign here, that is negative x squared. Okay, so we just have to find the variation of signs here. So negative to negative, there's none. Negative to positive, there is a variation of signs here. And positive to positive, there is none. So we can say that there is one possible negative root in this polynomial function. After finding the possible positive roots and the possible negative roots of this polynomial function, we can now proceed to finding the non-real roots of this polynomial function. So remember that we have to make a table. As you can see here, there are 2 or 0 possible positive roots. So also place here 2 or 0. And there's only one possible negative root. So we also place here one possible negative root. As for the total, remember that it's the highest degree of the polynomial function. In this case, it's 3. And remember that the total is the sum of the positive, negative, and non-real roots. So we can say it's 2 because 0 plus 1 is equals to 1. So we need 2 so that it will make it 3. Same here, 2 plus 1 is equals to 3. So we just need to place 0. So these are our non-real roots. Okay, now that we are done finding the possible positive and negative roots of this polynomial function, we can now head on to trying to find the possible roots of this polynomial function. So remember that p is the factors of our constant term, which is positive 4. And factors of positive 4 is plus minus 1, plus minus 2, and plus minus 4. As for q, remember that it is the factors of our leading coefficient, which is 1. So our only factor here is plus minus 1. Now we can actually get into solving the possible rational roots of this polynomial function. So as you can see here, we have plus minus 1, plus minus 2, and plus minus 4. Now that we have found the possible rational roots of this polynomial function, we can now try to find the actual roots of this polynomial function. And let us use factor theorem for this. So in factor theorem, your x will be whatever rational root you will use. And if f of x is equal to 0, then the rational root you placed here is a an actual rational root of that polynomial function. So let us use negative 2. In this, we have to substitute x with negative 2. So negative 2 cubed, that is negative 8. And this part, a lot of students get confused or they get a mistake, but this is actually quite simple. So you have to solve for negative 2 squared, which is positive 4. And there's a negative sign here, so that is negative 4. This is positive 8, and this is positive 4. Now, what I actually did here is I just canceled negative 8 here and positive 8 and negative 4 and positive 4. And now we got 0. So we can conclude that negative 2 is a rational root of this polynomial function because it doesn't have a remainder. Remember that we don't have to find for another negative root because it states here that there is only one possible negative root. So now we can try to find for the positive roots. Let us try to use 1. So we substitute x with 1. 1 cubed is equal to just 1. Negative 1 squared is equal to just 1. Negative 1. This is negative 4. And this is positive 4. Now we can cancel 1 minus 1 and negative 4 plus 4 because those just equate to 0. So now we can conclude that 1 is a rational root of this polynomial function. Now we just have to find for one more positive root. So let's try 2. Okay, so it got a little squishy here, but that is fine. So 2 cubed, that is 8. Negative 2 squared, that is negative 4. This is negative 8, and that is positive 4. Now we can just cancel 8 and negative 8, and negative 4 and positive 4. And now we got 0. So we can conclude that 2 is a rational root of this polynomial function. And since we already found the two possible positive roots, then we can say that negative 2, positive 1, and positive 2 are the rational roots of this polynomial function. So before I end this video discussion, I just want to address this possible mistake students make when solving for the roots of polynomial functions. So I already discussed the common mistake of students when it comes to negative signs. So I will be discussing this problem. This is a very common mistake wherein students interchange P and Q. I will just say that this should not be interchanged whatsoever because you will have the wrong possible roots of this polynomial function. So these are all wrong. So what you can do to solve this is to remember that P is the factors of your constant term, which is, in this case, positive 4. So the factors of positive 4 is plus minus 1, plus minus 2, and plus minus 4. And for the Q, remember that the Q is the factors of the leading coefficient. So in this case, 1. So the factors of 1 is positive plus minus 1. As for the solving part, it's straightforward. P over Q equals plus minus 1 divided by plus minus 1. It's equals to plus minus 1. Also here, plus minus 2 divided by plus minus 1. It's equals to plus minus 2. And same here, plus minus 4 divided by plus minus 1 is equals to plus minus 4. So these are the right possible rational roots of this polynomial function and not this one. So please keep this in mind. We have now come to the end of this video discussion. Thank you so much for watching throughout this video, and I hope that you were able to learn more about how to find the rational roots of a polynomial function. Again, thank you so much for watching, and bye!